How's everybody doing? So basically just wanted to continue with our Steac C malware analysis. So just to kind of review what we've done already, just to give you an idea of where we're at with this sample. The first couple of streams that we spent on Stealc C, we're looking at the obfuscation that this sample implements. So if I go to the main here, we have, sorry, not malware main, we want the actual start function. We have these string decryption routines. So this is pretty straightforward stuff where we had some XOR decryption occurring. And these were basically just with fixed offsets and globals. So yeah, so this basically was just doing some basic XOR decryption of the strings at runtime. And then it just uses input ciphertext and then a key. So this just does a basic XOR loop where it does modulus on the size of the key and then decrypts the original string in memory at a allocation that's made with local alloc, and then that's assigned to a global. So not only did we write automation to decrypt those strings, but we also wrote automation to assign their contents as the name of the global variable here. So then that gave us really easy and quick at a glance insight as to what string is being used where. So we do at a glance insight of like one of these globals. On the left-hand side here with cross references, we can see that this get lang ID is being resolved with this get proc address call and then assigned to this other global. And then if we look where that's used, then it's called in this other function that's used for a language check. So it was really important for us to not only decrypt the strings up front, also assign them to their respective globals, as in their string representation, but also there was this one level of indirection for these imports being resolved where there was these get proc address calls with their respective DLLs, and then those were also assigned to globals. So we had to write automation to resolve those as well. So now that we've done all of that, I spent a bit of last stream looking at some of these string copy resolution functions that are basically setting up these C++ structs. I don't know what C++ library code this corresponds to, but I won't spend too much more time on this because we kind of have a good idea as to what it's being used for here. But I spent a bit of time on that. And then we also started looking at the C2 command and control stuff. So first there was these calls to, let's go down here. Yeah, there was these string concatenations with generating a C2 address, and then they were using that to download a SQLite DLL here. And these are all those string copy calls that we reversed last time. There are C++ libraries. Again, we don't know exactly what libraries those are. And then this is very common for stealers to download a SQLite DLL in order for it to be used to access SQLite databases. And SQLite databases are commonly used by web browsers in order to store sensitive information such as form completion data and usernames and passwords. There's some browsers that are not doing this anymore simply because it's not the greatest idea because they're effectively like stored in plain text. But in this instance, they do use SQLite in order to read those SQLite databases. So another thing we looked at, I believe, is this get serial. These serial hashes are in this instance being used to so this is actually acquiring the volume serial, that being the C Windows directory serial number. So for that drive, and then it's using this hashing algorithm. This looks like it's a custom hashing algorithm for Stealc C in order to generate the respective hash for that serial number. And then that's being assigned to this variable that's then passed into this result that's returned after being formatted with this format string. So if we look at what that format string looks like a little bit closer, where it's initialized in that string decryption function, it's this long hex format that they're formatting that hash into. And then once they do that, then again, it's copied back into this result that's returned. So again, that's really commonly used to identify a system. So if we look at EAX here, it's being overwritten. So I think they're just using the result as the argument, or the argument that's passed here, the result pointer. So let's see where else this is used. Okay, so some of the arguments were messed up in this function. I think it might have something to do with this check stack that's created at the top of the function. We don't really have to worry about it too much, but some of the arguments might it might be a little bit more difficult. Do you maintain a document of discovered information like you're explaining? That'd be really helpful. Yeah, I do actually have that on our GitHub. But yeah, let me give you that document. So github.com invoke-re. We have our stream notes here. So you can just follow this repo and then you'll see whenever it's updated, but that's probably the best way. But I just threw it in chat there. And then the Steac C notes are here. So it goes over like all the automation that we wrote. And then another good way is obviously to check out our YouTube channel. So all these past streams are on the Invoke RE YouTube channel. So if you just search Invoke RE, I'll throw the channel in the chat there. But this is basically all of our past streams as well. Hopefully that's helpful. Okay, so getting back to this. Yeah, again, some of those arguments might be messed up. Some of the fast call calling conventions might not be 100% right in this instance, since this is indeed C++. And then there's a few others that were identified as this call. So, but we'll just kind of deal with it. So if we go back here from this malware main, we'll take a look at that later because I kind of got distracted by that last time since it is like the core stealer functionality. There's these other important functions that I do want to go through. So if we look at what this could be here, so there's those import resolution functions again that are doing get proc address in order to resolve runtime needed APIs. And then there's these subsequent functions that are called after the import resolution occurs. So if we look at what some of these are, so create DCA. So we're just going to have to look up some of these on the MSDN documentation, but this basically creates a device context with a specific name. And then if some of you who have Microsoft Windows experience, you might recognize these already, but get device caps will retrieve device specific information for a specified device. So we basically want to see what device this might be, and that corresponds to an index, and that index corresponds to, we might have this type information, but this corresponds to an enum, and then that enum corresponds to one of these. So the A value is indeed used quite often. So if I like hit the M key on our binary ninja database here, we can see like, okay, there's a whole bunch of stuff that corresponds to M. So not super helpful. But if I look at, but what this is actually the height. They're still missing types in Binja, unfortunately, for a lot of Windows stuff. So many enums and structs are common. Yeah, for sure. I generally use React OS code to find some of these enums, the project-wide rip grep returns. Oh, sweet, nice. Oh, cool. Thanks, Ms. Rack. Okay, horizontal size. So basically what this is doing is, so we can create an enum for this, just so I have it. So let's do import. We want to do create a new enum, and then we'll just call this device caps. And then I'll just edit this, and then we'll just do, so, okay, yeah, so that's why this isn't present in Binja, because they like struggle with these hash defines in their type parsing, unfortunately. Okay, and then now I can mark this up. That was painful, I know, but, oh, sorry, not 4. It's A, so actually B, so just to show you, 0xA corresponds to 10, so it'll actually be the vertical resolution, but still the same page that we wanted. So let me edit this enum, then we want this to be 0xA. I really just need to get like a actual solution for that because it keeps coming up. So then they're getting basically vert res corresponds to, so if we go back to this, then it's the height in raster lines of the screen, or for printers, the height in pixels of the printable area of the page. Basically, this is an anti-analysis trick that's just checking the size of the screen. And then if I look at this value as a decimal, it's just making sure that it's greater than 666 pixels. So we can just rename this to MW screen anti-analysis. And this is just basically for emulation and anti-emulation and anti-sandbox stuff. So some sandbox might not have a screen resolution of this size. So that's all that's checking for. Any idea why Microsoft doesn't include the enum values in MSDN? I don't really know. I think it's because they're, hey, what's up, Humpty Dumpty, by the way. I think it's because they're basically gearing toward developers and not like reverse engineers. But like if I just pulled this up, if I pulled up that enum value in Visual Studio and you like hover over the enum, then you can get the integer value. So the next function they call here is they're doing get system info. So if we Google that, info, that returns an LP system info structure or a pointer. So in Microsoft parlance in their API, LP just means long pointer to a given structure. So it's just a pointer to a system info structure. So if we just want to make this a system info pointer, then it creates that. And then it's just checking, like these offsets are messed up. Call, but like var 14. Okay. Yeah, so it didn't have to be a pointer because this is the address of this local variable. So then I just made that local variable system info. And once I did that, then it just gives me the struct member that it's accessing at the LP info structure is the DW number of processors. So again, this is another anti-analysis trick where they're basically checking for the number of processors to be greater than 2, which is also uncommon in security sandboxes, et cetera, because it's, like the more virtual CPUs you assign or whatever, the more resources you're going to use, et cetera. So either you would have to spoof this value that's returned from get system info, or you would have to do something else, just assign another virtual processor in order to pass this check. Or you could have a runtime hook for the get system info call, which I'm sure a bunch of sandboxes do. So we'll just do MW check num processors. And then let's look at this one. Okay, so virtual alloc x numa. So these are all pretty common. A bizarre trick. So like this is a well-documented anti-analysis trick. So let me see if there's actually, let's look at the actual documentation first. So it reserves, commits, or changes the state of a region of memory within the virtual space of the specified process, and it specifies the NUMA node for the physical memory. So I believe in virtual environments, either this call doesn't work or there is a different check that's done related to this. So they're basically getting the current process. I don't believe it has that many arguments. Let's see. Yeah, so these arguments are messed up too. Let's see if we can fix those, because these, it's folding the past arguments into the get current process call, which is incorrect. So let's see if we can fix that. I don't really know how to do that for a pointer call in Binja, actually. If anybody knows, let me know. Interesting, I thought NUMA was disabled on most normal computers. Yeah, let's just, instead of me looking at the docs, this is done by a lot of stuff, but so it allocates a large amount of memory, and if this API is not implemented, the process will terminate. So yeah, that's effectively what it's doing. And then in this instance, they're just acquiring the current process identifier with get current process, and then they're passing that PID. So if we look at the disassembly, it'll make more sense. So they're calling, oh, this is why, because the pushes occur before the call to get current process. But if we look at the docs again for virtual alloc x numa, it's getting past a process handle, and then so the process handle is going to be an EAX. So that's why it's pushed on last, because it's the first argument of virtual alloc x numa, and then the other parameters are the address. Okay, so then the first argument is the handle, then the address, then we have the size, the allocation type, et cetera, and then the NND preferred. I don't know what that is, so let's see what that is. Interesting. And then in the flags, it's probably specifying mem physical or something, I would assume. See here, it actually gives us the enum values, so I guess in some instances they do when it's on an index, I guess. Hex 3000, which is, I don't know what that value would correspond to. I need to double check, but because it doesn't correspond to either of these. Basically, they're calling an obscure virtual alloc technique that should work on most computers, and then if that doesn't work, then it calls exit process. So let's just call this virtual alloc x numa anti-analysis. Change the function signature won't work. So what's weird is like these are actual pointers. So these are like the runtime resolve functions, but I don't know how to do that with an actual function pointer, because this is like actually not defined. It just leads to this global. Like I assume I can't make this correspond to an actual type. I'll ask in the Binja Slack after this. But if you mean for the actual function itself, I believe get current function calling convention, then it's cdecal, which I believe is correct. So the function type. What do you mean IG? You haven't tried reversing in a long time? Well, you seem to know a lot, so appreciate the help. Okay, and then there's another call to virtual alloc with like a huge value, it looks like. So if I make this decimal, yeah, I think this is like just a giant memory allocation that is then passed to this function memset. And there, maybe let's just call it C memset void. Oh yeah, that's a good idea. Yeah. Okay, let's try that. So if we go back to the pointer here, so for example, this one, no, I don't think we can do that. Maybe like this. Yeah, I don't think so. There's probably some weird way to do it. I did it in the course. Okay, let me pull up those docs actually, because I did do it in my Binary Ninja course. Okay, so yeah, we should be able to do it like you said. Something like this, I believe. I think we just probably have to define it correctly, and I'm not defining it correctly. So we should be able to do get current process quite easily because it doesn't have any arguments. Just copy that function signature as an example, and then we can use that. So if I have like this one, so we do want standard call. I think I'm just going off the original Microsoft Windows function signature, but let's just do current process. And then this is going to be I see the pasted, so function signature remove. Just paste the functions. Okay. Yeah, I think that should work. Okay, so this returns a handle. I really just need to write something to do this. So I think that should work, which is easy in this case, but okay. And then if we go back here, now we have a non-code branch, non-code call. Why is this a null pointer now? Do I have to make this entire section? Okay, maybe that was a bad idea. I think I just need to ask the binge guys. Okay, let's just leave this for now, because, but yeah, I think we have the right idea. Probably just something I'm doing wrong. I think it's maybe because this section is not, I don't think it's executable. Okay, anyways, yeah, let's move on, because there's actually still a lot to get through. So this malware is pretty big, but I like solving these problems too, so. Okay, so the next, and then I think this is a just like memset routine. Yeah, memset to 0. I'll say cp memset. And then is it actually making the allocation? Or this would just be a stack address of that size, I presume. So if I pull up the stack view, we should see a gap there. Yeah, of 64 bytes. And then the value of 40 is passed here. Global memory status X. I don't know what this anti-analysis trick is off the top of my head. Let's see. More Googling. So first of all, this function retrieves information about the system's current usage of both physical and virtual memory. And then this returns a memory status X structure. So let's set that. Okay, so it's dividing the physical total used by, so this AUL, this is like a optimized function from Windows. I don't think it's an intrinsic, like this is actually a defined function. Unsigned long divide divides two UN64 values. The compiler might generate a call to this. It's just a compiler function for optimization stuff. So it looks like it is dividing, so it's accessing the D word and then accessing the next D word and then dividing them. And then dividing it by 400. So I don't know exactly what this is doing, but it's basically checking the physical memory using global X status X. So we'll do, okay. But yeah, so this is probably dividing it into megabytes like you said. And then it's just checking if the result is less than 100, then like a gig basically would be my guess. And then if we look at the last one here, we have a call to get computer name, which is, if we look at the docs here again, we have LP buffer and size. So that's just going to get this is just going to be the name and then the size, which this is just max path, I think, because it's 255 bytes to 260 bytes. So get computer name, and then, so it's checking for the computer name HAL9TH, and then if we Google this, then this is probably some sandbox default thing. So OSCI looks for it. So it's Defender related. So this is looking for Microsoft Defender. So we can just like add a comment like Microsoft Defender computer name, which I presume is in their like little emulation environment. And then John Doe, I don't know, probably corresponds to some sandbox. And this is the username. So MW get username, and then it's looking for John Doe. So computer name, username, anti-analysis. Okay. And then if we look at where that's called, or go back to where that's called, now we can see that those functions that are being called here are getting the username. So I'll just say username, computer name, and then those are being concatenated together here. And then opening an event with that value name. I think this is threading related. Open an existing named event object. So if there's an exception, then it breaks. So I think they're probably just using that to check if there's an existing one running, probably. And it tries to open the event, and then if that doesn't work, then it creates it, and then it exits. I think this would all be called after malware main, right? Yeah, so that's exception handling. And then we looked at this last time, but I think this is just setting up the stealer log. And then, yeah, this is just setting up the log structure with the system time. Oh no, maybe it's not. This might be anti-analysis too. It's kind of hard to tell what string this is generating with the C++ stuff. HU. So this is being used for, I think, just time stuff, right? The date, probably. And then this get value. Yeah, I would have to run this dynamically to see exactly what strings are being. Oh, maybe it's doing a date check, because this is 27/05/2024, and then it's being scanned into this format, and then these values are from the system time object. So get system time is the system time object. So let's see what value is being accessed there. If I can type, and then I was hoping it was going to be like relative values to the system time that were going to be populated here after I changed the object type, but apparently not. System time to file. Yeah, I'm pretty sure this is a date check. So null wait. So it looks like if this executes after 27/05/2024, would that be a date and a time? That's pretty cool. System time to file time. This is why static analysis is important, because like all of these anti-analysis checks might hit in a VM where you're trying to dynamically analyze it, or it might be past the date that it can no longer execute and all this stuff. So this is why we do the static analysis primarily, because it's so important. So let's say this is not the init log, but it is a expiration check, let's say. Okay, so then finally we get back to our malware main here. So always important to take a look at those anti-analysis checks, because if you can't get it to run dynamically, then that might be why, et cetera, et cetera. So, and it's kind of a good illustration of common anti-analysis techniques that are used by malware, either for anti-analysis in sandboxes or emulation environments, or your own virtual machines that you're trying to analyze malware in. Okay, so back to malware main. So again, we kind of got to that initial request for the SQLite DLL path that was written to file, default 100. I don't know what that is, but this is actually so like this global variable is reused a whole bunch of times. And then it looks like this is setting up the results that are stored in the C++ structure. And then this is more command and control stuff. These are all null bytes, I think. I don't know why these string copies have all this stuff, but it might just be like, I'm just changing these two chart pointers, but they're not valid ASCII characters. I'm hitting R when I select these to see if they're valid ASCII characters, but I can't remember. I just need a hex table. Or I could look at, actually the better way is probably to just look at the hex dump. Yeah, they're not valid. Kind of looks like ASCII art. Oh, it's white space. That's why it's not coming up. Definitely easier if I just look at a hex table, or ASCII table rather. Not a hex table, ASCII table. This is really tiny. 22 is quote and a space. Yeah, x20 is a space. Thanks. I don't know why hitting R isn't working on these. So I think this is just like a giant stack string. These offsets are being written to internet open A, and then this is the content type header for the HTTP request. Compares if the address is HTTPS, and then init alphabet global is this encoding algorithm, which I'm pretty sure is not base 64. And then it gets the system time. I don't know exactly what this is being used for. Oh yeah, I already marked that up. But it's getting, this is definitely the encoding algorithm. So this is used a lot. So it's probably custom encoding data, because this is not a valid base 64 alphabet. It has more stuff in it. Hail friends, Rust RE content. So Rust is very hard to reverse engineer, but yeah, probably some basic stuff. I use man ASCII for table. Oh, thanks. Yeah, definitely elfrans in the future. probably will look at some more basic Rust stuff for sure, because it's the decompilers and disassemblers are okay, but the decompilers get kind of messy. And there's a bunch of optimizations in Rust that make it hard to reverse. C++ has a great ASCII chart. Oh, cool. CPP reference. I made a Rust-lang reversing series a few years back. Oh, cool. Can we find that series anywhere, Mizrac? Okay, so I think this is probably their custom one. So let's do MW encode data custom. And then a new line. Again, if I just make this a char pointer, then oh, maybe I do have to make it. Yeah, so then that makes it a \r\n. Carriage return dashes. This is going to be our encoded data that's being appended. This is the resulting string, I think. Or let's just call it HTTP request. I don't know why they're constructing this, all the headers and stuff themselves, but more dashes, char. I wish you could just adjust this in bin just so I don't have to mark all these strings up myself. \r\n encoded data. Okay, so I guess they would construct this themselves in order to encode or embed this encoded data in a header. Not much, to be honest. Oh, cool. Bright programmer, Netlify. Nice, this looks awesome. I'm going to, I'll put this in the notes because I like keeping all this stuff. I'm just going to use Vim for the notes because I don't want to open cursor backup. I think I might have seen this before. Okay. But yeah, this looks awesome. I've been trying to learn some Rust too. I'm almost through the Rust book, so thanks for sharing that. That's really cool. Okay, so let's continue. So this constructs a custom HTTP header with this encoded data that is 20 bytes in size. I think that might just be a timestamp or something. And then it's opening the request and then just constructing more headers. I should probably actually reverse or mark these up properly so it's easier to look at. char4. So I'm just going to finish marking those up because it's kind of important. And then it's getting the size, it looks like. Wow, this is really gross. I guess that's what happens when I make the variable name like the content of the decrypted string, and it sends it. Okay, so while true, internet read file. Okay, so this is just like standard communication stuff. And then crypt string to binary A. Rust Under the Hood is a good book to learn about the optimizations. Oh, cool. Thanks, City. Yeah, it's a good idea. The LLVM stuff is pretty crazy. And the optimizations in general and the macro expansions and all that stuff. Crypt string base64. I think this might be base64. Maybe I was wrong about the encoding algorithm. This is decoding the response. So the third parameter. Yeah. Oh man, we don't have those values either. I'm just going to add to this enum, even though it's not 100% correct. Let's just call this Steac C const. Okay, so this is decoding base64. And then this first argument is going to be our string. And then that's probably going to be the length, I would assume. Oh no, that's the output buffer. That makes sense. It's called PB buffer. So basically it just, the reason it does it this way is it does the decoding to get the actual buffer length. This is like really common in Microsoft C programming. And then it creates the allocation. So this is the actual result. And then it decodes the buffer and then passes that back in this result argument. So this is going to be result 1. And then, so let's just call this, oh no, this is the wrong. So this variable is reused. So probably don't want to call it the content header, but that's okay. And then, oh, is it wrong about that argument? Crypt string to binary A. Oh, is that just the length? PB binary. Okay, so this is the result length. Okay, and then if we go back here, then there's like the response that's copied into the response, I believe. The result is concatenated and then added to a structure. This is just, and then this is the result structure, I think. And then see, like the cool thing about having, so for example, this base64 decoding function call, we can see like where else this is used, obviously. So if I click on MW decode base64, then we can see it's used in a whole bunch of different functions. These are probably all command and control related. So then we have an encryption key. Okay, no, there's other places that things are base64 encoded, but let's just say C2, and then there's other stuff here. So if, like we can kind of do what I mentioned earlier with MW internet crack URL, because that breaks up the URL. So it's probably better. Okay, so there's more decoding stuff here, but why don't we look at some of the actual Stealer functionality? Because that's probably more important than some of the C2 stuff, even though the C2 stuff is indeed important. So yeah, I like Rust 2, Sudi. Okay, so let's take a look at some of these functions. So, actually, let me finish marking the C2 stuff, as in just the high-level functions. That just reminds me that I need to go back and finish these, but you can see my ghetto function name application. Okay, so if I go back here, we can see a few different things. Oh, thanks for pinning that, friends. I just saw that now. We could probably, this is all C++ stuff. This is tokenizing the response. This is all like parsing stuff, so we don't reverse that. So if we look at the other function calls here, okay, so like this is probably some sort of format for Steac C, but it's tokenizing on this value, probably a delimiter and those C2 responses, and then more parsing stuff. And then, okay, so this is actually relevant. So basically Steac C has like two different components. It has like built-in Stealer stuff, and then there's dynamic Stealer stuff. So it gets like lists of plugins and a bunch of stuff to steal from, but we can look at the built-in stuff for this stream. So in this instance, they're looking at this Monero project registry path and then getting the wallet path. And then this function will do a heap allocation for, again, 260 bytes, and then it'll query the registry value at that location. So this is going to be the registry related stuff. I really need to figure out the types information stuff here. HKey current user. Once it gets the wallet path, it does .keys, and then that's a space. And then it also gets it from C data, gets the wallet path, and then it's probably going to just copy the data, I would presume. Yeah, so it reads the file. So here's just getting a file handle, gets the file size, and makes an allocation of that size, which is this var C here, and then reads the file. So we don't really need to mark up this function other than just saying wread file, and then it puts it into a structure with the string copy and the string initialization stuff we looked at last time. Let's call it wallet data. And then it sends it to the C2. So this is going to be our file upload. So it's what's kind of cool about like looking at the surrounding functionalities. You can kind of infer that like, okay, so this is going to be our wallet data structure, which is being accessed at some weird offset. So that's why it's not shown here. But okay, and then we delete the file after it's uploaded. More struct stuff, which I presume is to clean up because it's setting those pointers to null. Okay, so this is MW steal or just get. Okay, and then let's see. Okay, this might be our output file path. So it's doing sh get folder path. If we look at this one, then this is the CSIDL. Probably not going to have this here either. Where's the CSIDL for the second parameter? So then the argument folder. So get, and then this is the folder path. So it's getting 3 separate folder paths in this call based on a given argument. So this is going to be the folder path type. And then I don't know what these constants correspond to, but we can figure them out. All right, let's see if we can figure out these constants. It shouldn't take that long. All right, looks like we can use this. So 0x1c, local app data, then 1a app data, and then 2.8 profile. Okay. Okay, so I think these paths are being acquired for what reason? Let's see. Probably where to write the file data to. Okay. So once it gets the program data, so this is probably the path. Okay. So this, I hope they do some wraparound functionality in the decompiler. But basically this is getting the program data path and then finding a file within that path, copying it into a structure, get file attributes, and then, okay, so it's getting the wallet information and then encodes it and probably sends it to, yeah. Okay, so this is basically just searching for the paths containing wallets rather, and then getting all of the files within those paths. And it's getting those under these CSIDL paths. So app data, local app data, and the profile paths. So let's just call this a new line terminator, or is it Unicode? Yeah, it's just the null character. So those might be wide strings, which is why there's 2 null bytes, if that makes sense. Okay, so enum wallets in Monero. And then we have, where's that path call being made? Oh, I see. Does it actually have any arguments passed to it? Oh, it's probably doing this based on the results from the C2 call. Yeah, the C2 tokenized response. So actually, I think this is not just a generic wallet discovery functionality, but given wallets. Again, this is kind of hard to parse because there's a bunch of arguments pushed into this copy struct function. But we can kind of infer what's going on. So let's keep going. Anybody have any questions? You guys doing all right? Smooth. Okay, so this is doing more parsing stuff. It's good that we have these CSIDLs because now I can just fill these in here. Oh, we don't have 10 yet, do we? Okay, this is getting the desktop. I has much better database for enums. Yeah, definitely. I 100% agree. I think they're trying to fix it, but there's still a few missing. Local app data. Okay, so again, I think this is just enumerating directories for stuff to steal, and then putting the copied strings into a global app data, documents, profiles, programs. Okay, so I don't know exactly what those paths are being used for, but I think it's based on these tokenized results. Okay, see, like this is based on the CT response. So this is going to be our CT response. We probably actually have to look at a CT response to get a better idea of exactly what this is being used for. Okay, find first file, co-initialize, concatenation. What's this function? Why don't we have this one? Path match spec. Get file size, read file. Okay, so this is doing more upload stuff. And this is getting the 7F0, 1, 2, 3, 4. So let's just say it's %s, co-initialize, co-create instance. Okay, so this is doing column object stuff. So let's see what CLS is referring to. So I think there's a plugin for this in Binja. Maybe not, fairly certain there. Companion in this thing. And then let's just review how it works again because I can't remember exactly. Column objects. And does this work? So, okay, so just to back up a little bit, Windows has this concept known as the component object. It's quite complex, but basically it provides an interface to interact with operating system components. And it's a binary standard developed by Microsoft that is reusable software components to interact with runtimes, allows code reuse, et cetera, et cetera. So whenever it's being used in this way through the C interfaces, essentially these COM interfaces are created in order to interact with operating system components. So if we want to figure out what operating system component is being used, then we need to actually figure out what the COM identifier being used is. So if vtable representation, import from GUID, companion plugin, first it searches for, okay, how do I do that? Calls co-create instance, okay. How do I use it? Does it need to restart? Oh, maybe. I hope I don't have to reanalyze the database because that would just make it not usable. And hey, what's up, Lopsec? Good to see you. Okay, let me reopen the database. Oh wait, tools. Okay, so plugins, companion, apply types. Okay, it might be working now. There we go. Look at that. Man, that's so nice. There's definitely nothing like that on IDA. Oops, I did not mean to close the database. I was trying to save it. Okay, so this is a iShell link interface. And then I can't remember what the iPersist file interface does. Reference. Retrieves a class identifier. What? Oh no, this is a part of iPersist file. So what function is it calling with an iPersist file? Okay, so this is the interface. iShell link A. Maybe this GUID's wrong. I already applied them. Okay, iShell link A. Okay, there's a whole bunch of relevant functions, but I don't think this is iPersist file. Run as. Oh, it definitely looks like iPersist file. Yeah, I think those GUIDs wouldn't map to multiple things. So enables an object to be loaded from disk rather than storage. It's like stream stuff. But why does it need to use the iShell link interface for that? Create, modify, and resolve shell links. Yeah, like I know this is commonly used to access link files, but like I need to get these. Okay, maybe that was wrong. Hold on, because this will be the iShell link. Basically, okay, so I'll explain this a little bit better. So co-create instance is just getting a shell link interface. So if we look at what co-create instance is, it will actually create or define a single object from the class associated with the specified CLS ID. So CLS IDs are just basically system GUIDs that Microsoft uses to define interfaces. And then so this is just going to be a iShell, is it iShell link A? And then vtable resolved, get path, get description. Okay, so this is just using, so this resolves a iShell link A interface. And then I changed the device type to that interface. And then this has a query interface function that's used to acquire iPersist file. And then that's used to get the path and description for a given link file, I believe. So that's all this is doing. I just wanted to make sure it wasn't doing anything crazier, because you can use com for a whole bunch of stuff like privilege escalation and get link lnk info. And then this is going to be null. So this follows link files to steal more stuff, basically. What I could. So I think this is going to be like harder to analyze for some of this more dynamic stuff. Yeah, see, so it's looking for LNKs, and then it'll do the walk LNK stuff that we just reversed when there are indeed LNKs that it needs to traverse. Okay, and then it does that based on this tokenization stuff. So let's do more concurrency stuff. All right, any questions? Com used to con. Yeah, nice pun. Okay, so I just called that MW read response steal info from paths, because that's effectively what it's doing. Again, we're not entirely sure what those paths are just because we don't have a C2 response, but that's okay. Any questions about that before we move on to the other stealer functionality? Any gamers in the chat? They're stealing Valve stuff. This is our HKey current users, and then they're going to get software, Valve, Steam. They're going to open that key and then get the Steam path. This is going to be, yeah. And they close the key, and then they create, they get the config, SSFN star. I don't know what that is. Okay, this is all Steam related, so this is important. So I'm just marking these up so that we can see them easier. See, so now we can look at the string compares, and then there's basically it's enumerating a directory with find first file. Question, looking at around for Stealc C samples, I found some packed and some are not. Was a sample packed? I'd prefer to start with a sample that's not packed. So the one that I linked in the chat is the unpacked one. So if you don't have a malshare, account, that hash is also on UnpackMe, which you can register for free, and it's also unpacked. So this one's a little bit harder because it's C++. So the other Stealc C samples, the reason it's called Stealc C is because it's just C. So it's this one's a little bit harder. So that's why there's like all this concurrency and all the C++ boilerplate that I'm having to deal with, but it's not terrible, especially because I'm just not dealing with most of it. I'm just looking at the core functionality, but hopefully that helps. Okay, so this is looking for soft Steam and then reading the file and then passing. So enum Steam directory. Perfect, thanks so much. I'll use malshare. Okay, I'll try to find the C only sample as well then, yeah. Yeah, it shouldn't be too hard to find a sample on Malware Bazaar or something. But if you can't, just ping me. I'll be happy to help. Okay, so let's see. Okay, yeah, so it's looking for these different files within the Steam directory. So this config.vfd, potentially sensitive information. Okay, controller files, whatever that means. Dialog config. So yeah, probably all sensitive stuff. Login users, also sensitive. I thought there was some memory stuff that it does too, but maybe we can find that elsewhere. Oh yeah, here it is. What do you really think? What do you really look for when reversing malware? Like ransomware, we know we need to look for the file encryption algorithm so we can reverse it. In these cases, what are we mitigating by looking at these things? One purpose, I think, for reversing non-ransomwares is their detection. Yeah. So in this instance, like when I started off looking at the sample and I decrypted the strings, then I got the command and control address. So if you found this like at your company or something, then you could search for that IP address being contacted in your environment. Other things that, like, say you had a breach and you were infected with Stealc C and you wanted to see what files were stolen by the stealer, then that's another good thing to look for. So that would be like what we're looking for in this instance. So yeah, basically looking for the infection routines that the malware is using, and then what data is exfiltrated is often what like folks are reversing stealers for. Because you basically, like, if you're infected with a stealer, you want to know kind of what's being stolen and why and stuff like that. Hopefully that answers your question. Okay, so I'm gonna run to the washroom because I just drank a bunch of water and coffee. So for those of you who are new here, we do malware analysis training. That's why I can do these free streams and put out all this free content on YouTube, etc. So if you check out training.invokere.com, we have like full trainings on Binary Ninja and IDA. So I'll put that in the chat. And basically just walks you through all the things that I'm doing today. So dealing with like kind of zero to hero stuff. So setting up your virtual environment, the portable executable format. It's only for Microsoft Windows that we're looking at malware for in this course, but still gives you a good idea of what level concepts you need for reverse engineering. And then we go through everything from static to dynamic analysis, network monitoring, obfuscation, etc. So I'm just going to play a quick ad for the course while I run to the washroom, but I'll be right back. Hey everyone, my name is Joshua Reynolds, and welcome to the Invoke RE Introduction to Malware Binary Triage course. Throughout this course, you will learn to triage and reverse engineer malware binaries using a number of proven techniques. These include static analysis, which is the concept of analyzing malware at rest, and dynamic analysis, which is the concept of analyzing malware as it executes. We will also be analyzing network protocols used in malware command and control communications, malware obfuscation, packers and how to unpack them, process injection, how to write effective YAR rules to detect malware variants, and how to compare malware samples at a binary level. This course consists of 11 modules, each containing lectures and practical labs to apply knowledge that you have gained as you complete the course. We provide both video and written materials, so no matter what your learning style is, you can complete the course successfully. Thank you for checking out the course, and we look forward to teaching you. All right. Yeah, and developing detections is also something else you want to do commonly with reversing malware. So seeing how they persist, the functions they call in memory, and what sequence they call functions, etc., etc. So I forgot to mention that. Let's continue with a sample. So we have some in-memory analysis routines looking for steam.exe, and by routines I mean one of them. So if I click on this function that's passing steam.exe as the argument, then we have the steam exe name. Then we have the process 32 first. So this is enumerating this process snapshot. So this is just getting a snapshot in memory of all the processes that are currently running. And then the result of that snapshot is passed here. So let's just proc snapshot, something like that. And then that snapshot's being enumerated for processes using this process 32 first and then process 32 next. And then that's just being compared to the string steam exe. So current process. Basically it's looking for steam running in memory, steam process, and then the result of that. So it's returning the value. I think this is a struct, so I need to type this correctly. So if I change this to a process entry 32, maybe that exists, then we can see the th32 process ID, or the process ID of the process, is being returned. So this is just getting the steam process ID. So let's change that. And then that's being passed as the argument. So steam process ID. And then the process ID is being used here. So it's open process. So this is just opening the string copy A. Let's see here. I don't know if that's the result string, but let's just use that for now. And then so it opens a handle to the process. And then it looks for this constant value, I believe, in the memory. So let's see. So let's see what's passed. So okay, so we have the process handle. Let's just call this H process. And then we have the search pattern. And then we have the, not sure what that is, LP base address. Okay, so yeah, it's reading the process memory. I think this is just converting it to bytes, because it's just using read process memory. So I thought it was actually manually going to walk the sections or something. So it reads the process memory, and then it just looks for that value. It's all C++ stuff. And then encodes the data that it finds. So let's Google this constant value. It's probably something important. Let's decode it first. So I'll just so you guys can see what I'm doing. And let's use that from hex. Okay, so it looks like that doesn't really help us too much, but that looks like base 64 to me. So if I do from base 64, okay, it's this JWT tag thing. So let's Google that. Okay, so it's some sort of key that it's looking for in memory. Steam token, some Chinese forum. They talk about this. Let's not worry about that. But it's getting some sort of ED25519 elliptic curve, Diffie-Hellman key exchange. So maybe a signing key or something. So let's say Steam key constant. So I'm just going to mark some of this up, and then we need to, this encodes it, cancellation token registration. Okay. Oh, this might be different. And then, okay, Okay, it just ensures that it's a certain length, and then it returns the result. So let's do malware search for Steam val get key, something like that. Okay, and then we'll do MW like that. Okay, cool. So and then they upload it. So this is going to be the key data. Again, weird offsets with the structs. So we'd have to get those exact offsets, but we have a good idea of what it's doing now. Steam tokens. I don't know why I didn't make this a string, but how long is this? I thought I could just make this into a whatever. So 20 bytes. If I make this, it's gonna be too long, right? Yeah. Oh, I see. That's why that was happening before, because they're W chars. 10. I'm just gonna make this a regular char, right? W char 32. Okay, there we go. Okay, so steal Steam token from memory. Let's keep going. Okay, so this is gonna be steal Steam. This is probably gonna be a struct offset on the stack as well. So let's see. Yeah, this is probably a big config structure. So if I see where steal Steam is used, then this is probably initialized somewhere relative to this. Okay, we could probably clean up the on stack config structure later. Okay, so local storage level. Okay, so this is Discord, probably Discord tokens. So it's the app data path, local storage level, current. So if I see what the string actually looks like, then it's looking for, again, just marking up those strings. Okay, so it just uploads all of that stuff. And then, yeah, it's adding it to this large structure. But this S is going to be, that's going to be steal Discord and then steal Steam. Let's see what this is. Okay, Telegram, upload file data. So this is just enumerating specified directories and then uploading the file data. Again, these are probably structures that are arced up. Telegram. I wish we would just merge these. I think we can merge them to local variable names. But yeah, so this is basically enumerating Telegram directories that contain key data. And then we have, okay, so this is steal Telegram. Why can't I change that name? Okay, so this one's going to be, let's see, Tox. I've never really heard of Tox chat, but so we could probably fix those struct offsets later so these arguments and stuff make more sense. Okay, and then we have another check stack here, so I just need to change this offset to be, let's see, this function is massive. Okay, so this is Microsoft Office stuff. Another check stack. I definitely need to file a bug for this because doing all this every time is annoying. Okay, this function we didn't add, reg enum value a. WTF is this? I'm looking at some malware that steals information from a computer. And I'm doing that using a program called Binary Ninja to look at the instruction code in order for me to understand it. And then this program basically like lets me mark up the instruction code in order to better understand what I'm looking at as I go. Hopefully that makes sense. That's fine. Sounds good. Okay, so this is all string parsing stuff. Like I don't know how much of this we need to look at, but this is going to be collecting Microsoft Outlook information. This is all vector stuff. So like this is all C++ stuff. Do you work as malware analysis analyst or is it just a hobby? Yeah, I do. It's basically my company that does this. So you can check out our website. Also as a hobby, basically always. But yeah, that's how I put food on the table, as it were. Okay, so let's see. Okay, so let's do, basically this is string concat stuff, and then it's uploading these files that it's enumerating for Microsoft Office and Outlook. So let's look at some of these decrypted strings to see what they are. Okay, so they're just Outlook profile paths. And then looks super interesting. As a developer, cool to see the other side. Yeah, thanks for hanging out. I appreciate it. Okay, so let's just call this, oops, let's go back here. Is this doing the upload in here? Colon, okay. I just want to see where it's doing the actual, okay, so this is converting an integer. And then this is just %d, so that's why I realized it's an integer. Okay, and this is all these control characters. Not control characters, but all these wide chars everywhere. Okay, so probably don't have to look at this too much longer, but basically it's acquiring profile information from Microsoft Outlook and then uploading it. And then, okay, so we already looked at that. I just wanted to see where it was doing the upload in this function, but it's probably buried. Yeah, we won't worry about it because we understand what it's doing. And then it creates a file called outlookaccounts.txt. Pretty straightforward. Okay, this is where it's doing the upload. Cool. Okay, so steal, what's this one doing? Pidgin. Does anybody use Pidgin anymore? I remember using that back in the day. Okay, Okay, and then I think this is doing a screenshot and then converting it to a JPEG. So like if we were to Google all these, basically it's just like a strenuous process to get a screenshot of Microsoft Windows from the C API, but basically they're doing get desktop window, they create a rectangle, they get the device interface, like kind of what we saw earlier in that anti-analysis trick, and then they're creating a bitmap, they're selecting the object, and then they're getting this GDIP, I think this is a stream, a bit stream or something, creates, why can't I read this? Creates a bitmap object based on the handle, and then basically it creates like a bitmap of the whole screen, I think is how it works. And then it just saves it to a file. So save GDIP or GDIP save image to stream. And then it gets the size and then uploads the image using that data. So pretty cool. Okay, get screenshot. Let's see what else this is doing. I don't think that's right. What's A in that? Oh, did I close that directory or that article that had those mappings? Oh no, that's encoding the actual result. Windows system DLL. Okay, let's just call this like the same. So space, and then, okay, so this is just doing download and execution, I think. Because if we look at what this is doing, shell execute A, yeah, let's just make sure that this is actually downloading something. Yeah, it is. And then shell execute A with the result. Okay, where else was shell execute A being used though? Because that's important. Okay, module name. Okay, this is self-deletion. So, okay, so this is kind of cool. Like, so after all the Stealer functionality runs, this would get the file name, its own file name, and then it would create a little bat script containing this string, which if we look at the actual string here, basically it'll be this C timeout string and this delete string. So we didn't exactly find it during our analysis, but that SQLite DLL is being written to this program data directory. So it's just doing star.dll to delete all of those. Then it sets a timeout and then it deletes itself. So basically it will execute this bat script at the end. So like if I look at this self-delete, then basically that's what this is doing. Okay, so this is going to be string compare self var1. Okay, let's just call this, and then, so that's important to know, right? Because if they are doing self-deletion, then that makes forensics harder. And then if they are doing download and execution of additional payloads, that's also important to note for our malware analysis. And that's kind of it. So aside from the Stealer functionality, we didn't know because of the parsing that's being done in those command and control responses. We were basically able to determine that there's Steam files that are stolen, there's Discord tokens, there's Telegram data that's stolen, Tox data, Outlook data, Pidgin data. A screenshot's acquired, then it'll download and execute additional commands and then self-delete. So that's kind of what I wanted to get through today. I know the decompilation doesn't look perfect, but sometimes it's better to just try and get through the main functionality of the malware rather than trying to mark everything up perfectly. Let's go in our notes here, and then I'm just going to add what we did today. So today's the 22nd already, wow. So analyze remaining Stealer functionality. Steac C will steal. And then we'll just say, make this a bullet list. Steam, Tox, Outlook data. What else do we have here? Just want to make sure I don't miss anything. Oh yeah, Monero too. Monero wallets, Discord, tokens. Did I get Telegram? Nope. Telegram data, Pidgin. In addition, it will take a screenshot, and has the ability to download and execute additional files. So if I go into the download and execute stuff, I do want to see if, okay, so here we can see that okay, so I don't think this is an alphabet encoding. It's probably okay, that makes more sense. So it's getting the system time. This is actually getting the system time to create a random string. So that makes more sense. Or let's just say get rand string. See, because it's getting this length in bytes, so 10 bytes in length. So here we have app data temp, then it's getting a string that's 10 bytes in length, getting the .exe extension or a .dll extension, and then this is the payload type, and then basically it'll either, if it's a DLL, then it uses run DLL 32 to execute it. But then if it's a exe, then it just executes it with shell execute. Then there's also this flag that will specify whether or not it runs it with open or run as to run as a different user. Okay. So yeah, that's all I want to verify. So like this is really good stuff for if you're looking for this type of functionality or this malware functionality in your network. Like you know that a payload is going to be written to app data in temp with a random string that's 10 bytes in length, and then whether or not it's a DLL or executable. And then now we know how the payloads are executed with run DLL or shell execute. So all really good information to know for like detection and hunting and stuff like that. So yeah, we could say that. And then we could put the format here. So something like AZ, what was their custom alphabet, this thing? So we can just say 10 in length .exe or DLL. Okay. So yeah, that's like the majority of the Stealer functionality, other than, again, those custom responses that are stolen and sent to the C2 server. But I think that's probably good to wrap up Steac C. Binary Ninja loads the binary attempts to... Oh, I see. Sorry. Yeah, thanks, Seti, for answering the question. Yeah, so this program, so yeah, like Seti said, Binary Ninja basically interprets the binary code, lifts it into... these machine instructions, which this is x86. So these are Intel CPU instructions, and then it'll lift them further into this like pseudocode representation format. So it's like kind of a pseudo C format that I can use to work a lot faster than just looking at the assembly code, if that makes sense. Thanks, Eddie. Appreciate it. Cool. Yeah. So again, if you're interested in learning how to reverse engineer with Binary Ninja or IDA, definitely check out our training. And I'm just going to play the ad one more time before I take off, but I'm going to upload all of these notes onto our GitHub here. So they're going to be, all the stream notes will be here. And then basically we just give all these, like this reverse engineering database and stuff to the training students who we just have like a premium tier. So if you are interested in getting access to this reverse engineering database that I just worked on, you can check out the premium stuff too. But okay, so yeah, I'm just gonna run a quick ad for that, and then I'll be right back. We're gonna raid somebody because it's always good to pay it forward. So, but before I do that, actually, just remember:
never give up. Never give up. Never surrender. Never surrender.
Never give up. Never surrender.
Never give up. Never surrender.
Never give up, never surrender.
Never give up, never surrender.
Oh, shut up.
No, never give up, never surrender. Never give up, never surrender. Damn the resonance cannons in full speed ahead, huh?
So never give up, never surrender. I know some of your jobs might be hard, but just keep going and it'll get better. So yeah, I'm just going to play that ad real quick and then we'll raid someone. One sec. Hey everyone, my name is Joshua Reynolds and welcome to the Invoke RE Introduction to Malware Binary Triage course. Throughout this course, you will learn to triage and reverse engineer malware binaries using a number of proven techniques. These include static analysis, which is the concept of analyzing malware at rest, and dynamic analysis, which is the concept of analyzing malware as it executes. We will also be analyzing network protocols used in malware command and control communications, malware obfuscation, packers and how to unpack them, process injection, how to write effective YAR rules to detect malware variants, and how to compare malware samples at a binary level. This course consists of 11 modules, each containing lectures and practical labs to apply knowledge that you have gained as you complete the course. We provide both video and written materials, so no matter what your learning style is, you can complete the course successfully. Thank you for checking out the course, and we look forward to teaching you.